Hello, and welcome to this session on practical HTTP header smuggling, where we're going to look at some of the ways we can sneak HTTP request headers past reverse proxies, and some of the fun vulnerability exploitation we can get as a result of that. But before we jump into that, we need to have the mandatory Who Am I slide. So hello, I'm Daniel Thatcher. I work at a company called Intruder. We're a cloud-based vulnerability scanner focused on making continuous monitoring easy. I work there as a researcher, as a penetration tester, as well as providing some of the security expertise for the platform. A lot of my research is focused on black box scenarios, as these are the ones I find myself working in most often, and to me they tend to be the most interesting. I've also got some links to our social media and our research blogs, which will be available at the end of the presentation as well. So what are we going to talk about today? We're going to start a review of the model that we're using to describe a modern web applications architecture. We're then going to move on to discussing what is actually header smuggling, some talk about the detection of header smuggling, and then a look at some applications. Finally, we'll finish off talking about how to defend against header smuggling, and some conclusions and talk of where the research can go in the future. So how is a modern web application set up? Well, we're going to model it in this talk as a front-end and a back-end server. The front-end server is typically responsible for duties such as caching, load balancing, or acting as a web application firewall, whereas the back-end server is what actually runs the application's code and logic, is responsible for accessing all the data of the application. Now, it's really important to mention that this is just a model. And in most scenarios, including the ones we'll see today, it's actually a massive oversimplification of reality. However, this model allows us to understand a lot of behavior we see, and it allows us to move forward with exploitation by assuming the setup is like this. But if you find yourself in a situation where you're trying to understand some behavior, this is an assumption worth challenging, as usually the front-end servers could be a chain of more servers, there could be multiple back-end servers, or the setup could be more complex than this in ways you couldn't even imagine. Now, generally, front-end servers use HTTP headers to pass information to back-end servers. A great example of this is the exported for header, which front-end servers typically put the client IP address in so that back-end servers can know the initial IP address from which the request originated. This makes it quite important for front-end servers to actually filter out headers such as these from the client's request. Otherwise, as a user, I'd be able to put whatever value I wanted into the exported for header and spoof my IP address. So if the information in these headers is to be trusted, the front-end server needs to validate it and filter some information out if it was provided by the client. We also get some interesting situations when the servers disagree about either the value or the existence of a header. So one we've seen a lot of in recent years is request smuggling. When servers disagree about either the value or the existence, the content length and transfer encoding headers, this can often lead to request smuggling. Similarly, we'll also look at a situation in this talk where this leads to cache poisoning when two servers disagree on the value of a header. Now, with that in mind, what actually is header smuggling? Simply put, it's the process of disguising a header so that it will be passed differently by different web servers. And in this research, we're going to focus on the situation where the front-end server misses a header or doesn't pass it in the way that the back-end server does. And then the back-end server passes it as we want it to, without the front-end server modifying it. How do we disguise headers? Well, we're doing what I term as a mutation, which is simply a modification you can make to a header to cause different servers to pass it differently. So some examples of mutations include the identity mutation, where we do nothing to the header. So this xMyHeader test header here will look pretty much as you'd expect a standard HTTP header to look. However, if you use underscores in header names, it's quite common for some servers to process it as though it was the xMyHeader test header we had on the last slide, whereas some will see it as a different header. Similarly, one we see a lot in request smuggling is putting white space in places around the header, for example, here before the colon. And it's worth noting at this point that a lot of these mutations come from request smuggling research, as you may have recognized already. Another one we see quite commonly is white space at the start of the header. And one we're going to see a lot of in this talk is including some random junk in the header name after a space. So some servers will pass this header as a header called xmyheader abcd, whereas others will just pass it as a header called xmyheader with a value of test. So this research set out to find a methodology for detecting header smuggling, and there were two key aims of this methodology. The first is that it would identify mutations in a generic way, where you find a mutation independently of a header. So once a mutation has been found, we can apply it to any header to sneak it through to the backend server without being recognized by the front-end server. The second aim was that it would work in black box scenarios. As I mentioned at the top of the talk, these are the scenarios that I find myself in most often, and personally for my research find most interesting. So these are the ones I chose to focus on. Now I'm going to explain the methodology through the use of an example. So the methodology works by testing one mutation at a time and trying to determine whether it can be used to achieve header smuggling. So in this example, we're looking at the mutation which adds an ABCD after the space to the header name, and we're going to see if the front-end server will process this as a header other than a header called xheader, while the backend will still see it as the xheader header. So to start off the detection process, we use what may look like a fairly normal request. The only thing that might stand out to you about slightly strange in this request is that it is a GET request, but it has a content length header in there. And the value of the content length header is set to 0, so we're actually not including a body. Now, most servers are completely fine with this. So as we can see here, we get a 200 OK, indicating the response we really expected for a GET request to the home page. The next step is to put an invalid value in that content length header. And as we can see here, unsurprisingly, this causes an error. This indicates that one of the servers in the chain is trying to pass the content length header, and when it sees an invalid value, such as the Z here, it's going to throw an error. Now we repeat this process with our mutated header. So here, again, we're putting this content length value of 0 in the mutated content length header this time, and we get a response that we expect without any errors. Now, when we put an invalid value in there, we again get an error. So we know that some server in the chain is passing this. Now, there's a couple of key things to look at here to determine whether we have header smuggling. The first is a comparison between our requests that set the content length to 0. It's quite important that these set the same response, and using this, we can know that our mutated header hasn't been so malformed that one of the servers in the chain has rejected it or refused to pass the request completely. Every server has continued to pass the request as a valid HTTP request and return the response we expect. We also need to compare the errors. Now, importantly here, with our mutated and unmutated header, when we put an invalid value in them, we get different errors. And this suggests that the errors are coming from different servers, which are erroring when they see an invalid value in the content length header. So one of our servers is reading the content length unmutated header, whereas another one seems to be passing our mutated header. Now, as we know that the server, which is likely the front-end server, which is passing the unmutated header, is not throwing an error for our mutated header, as we're getting a different error back. This suggests that that second error for the mutated header is coming from a back-end server, which is reading this while the front-end is ignoring that mutated header. So we have a mutation which allows us to sneak a header through to the back-end without the front-end seeing it. Where do we get from here? Well, sometimes we might know a header we want to test already and sneak through. A great example of this is the x-forwarded for header, where if we're coming across some IP restrictions, this might be a great candidate to try to sneak through to the backend to bypass these restrictions. However, often we don't know a specific header, which will be interesting for our target system, and we just want to try guess as many headers as possible. Now, for this in my research, I've been using an updated version of James Kettle's param miner extension, which I will be releasing as well as part of the research at the time of the conference. What this updated version will do is it will search for mutations which allow us to sneak a header through to the backend. And then with each of those mutations it finds, it will try every header that param miner will try anyway and see if it can trigger some interesting behavior. So we're going to look at some examples now. And the first one of these examples is in AWS API Gateway. Now, API Gateway is a service from AWS which allows you to build HTTP APIs built on Lambda functions, which are AWS's version of serverless functions. In essence, you run the code for your function without having to maintain any of the infrastructure, and you only pay for the execution time of your function. Now, if you want to limit IP access to one of these functions or one of these APIs, you use what's called a resource policy, which you apply to your API Gateway service. I have an example of the resource policy here, which may be of interest to some of you more familiar with AWS. But the important part here is that only the IP addresses 1.2.3.4 and the range 10.000/8 are allowed to make requests to this service. Unfortunately, I don't own the IP address 1.2.3.4 and can't send requests from it. And in this example, we're sending requests from outside the customer's cloud account. So there's no way I can send from that internal range either. Now, if we set up an API with API Gateway and apply this resource policy and send a request to it, we unsurprisingly get a 403 forbidden because we're not requesting from an allowed IP address. Perhaps slightly naive approach might be to just include the x44 header in our request with an IP address on the whitelist. And unsurprisingly, this doesn't bypass AWS's restrictions. It would be nice and it's always worth testing, but I don't think that's going to come as a shock to anyone. However, through some testing, I discovered that I could sneak headers through to the backend by using this mutation of adding some junk after a space in the header name. And the backend would still parse it as though that space and training characters weren't there. So I tried the following request, and I got through to my API, bypassing all the restrictions. So that's quite a nice start, but often we won't actually know an IP address which is allowed through to the API. We might be able to work it out, but we'll be blind guessing quite a bit, and that's quite difficult. So I moved on to trying something perhaps more stupid, but putting an invalid value in there that can't be passed as an IP address, in this case, the letter Z. And quite fortunately, this also worked. So to summarize that, we could bypass IP restrictions in API Gateway resource policies by adding this header in the slide to the request. Another similar example that I also reported to AWS was in Cognito, which is used for identity management. Now, Cognito, on a penetration test that I was working on, their Cognito instance was limiting access to the client. Well, it was rate limiting you. So if you sent too many requests, I believe it was 5 within a short period of time, your IP address would get blocked for a while. However, I've discovered that if you add the x44 header that's a vertical tab after the colon you can see in the slide there, and then any other value, you would no longer be blocked and you'd get 5 more requests. It's important to note here that you couldn't cycle the value of this header, including valid IP addresses, and you wouldn't get any more requests. So this is a very minor bug that takes your limit from 5 requests to 10 total within a short period of time. However, I feel it's quite a nice demo of what can be done, and even though the impact is minimal, I think it's worth mentioning, just as an example. Another example we're going to look at today is cache poisoning. So I reported the issue with bypassing the resource policy IP address restrictions to AWS, and they fairly promptly fixed it. However, I noticed that I could still sneak headers through to backend servers using that same mutation of adding a space and some trading characters. So I started to think about what else could I add here that could be interesting. Now, there's probably a lot of headers internal to API Gateway that would be interesting if you knew them, but I couldn't find any. However, one that perhaps is quite interesting is the host header, as it's a bit more fundamental to the request. So I set up 2 APIs to test with. The first one you can see here is this victim API, and a request to /a on this will just give you real response A. The second API is this attacker API, and for reasons we'll see in a second, this responds with poisoned A when you request it. So the question is, what happens when I send the following request? Here we have two host headers, an unmutated one, which is for the victim API, and a mutated header, which is for the attacker API. Well, it turns out API Gateway will give us the response for the attacker API, this poisoned A response. So this becomes interesting when we introduce a cache. To test, I set up CloudFront in front of my API Gateway instance, and I set the all viewer request policy, which effectively means that CloudFront will forward all headers to API Gateway. I then sent the request from the previous slide. Now CloudFront doesn't pass this mutated host header, so it sees the host header for the victim API, and it thinks the URL is for the victim's API. However, API Gateway for this request gives us a response from the attacker's API, which the attacker controls in this scenario. What happens as a result here is CloudFront will cache the result under the victim's API cache, but the response will be completely controlled by the attacker. This allows an attacker to target a victim using CloudFront or any other caching proxy which will forward these headers in front of API Gateway and just overwrite any responses in their cache with any value completely under the attacker's control. Now, we're also going to look at CL.CL request smuggling, i.e. request smuggling based on two content length headers. Now, a lot of request smuggling recently has been based on the use of a transfer encoding and a content length header. However, at Black Hat USA 2020, Amit Klein presented a bug in Squid and Abyss, which was based on two content length headers, one of them being mutated. Now, he detected this through white box testing, but I was curious about whether it was possible to detect these sorts of bugs through black box testing, and importantly, whether it was possible to do it safely. So those of you familiar with James Kettle's detection techniques based on timeouts for request smuggling might be wondering why we can't just adapt those directly. The issue is when you're looking at CL.CL request smuggling, if you don't know which server is going to pass which header out of the front end and back end server, you have a 50% chance of causing a timeout in a vulnerable system, but you also have a 50% chance of leaving some data in the socket and affecting another user's request. And this is something we generally want to avoid. So just to recap the setup, we have Squid acting as a front end, doing some caching in front of Abyss. Now you can exploit this bug to do more than caching. You can directly affect other users' requests. However, I'm showing caching here as I think it's the nicest sort of simple way to show this bug. Now, so the bug that Amit Klein presented looks like this. We start with a fairly normal post request shown here in green. The only slightly strange thing about it is we have two content length headers. One unmutated content length header, which says the length of the body is 33 bytes, and one mutated content length header, which says the length of the body is 0 bytes. Now, what's going to happen is our front-end server Squid is going to read our unmutated content length header and believe that this is a post request with a body of length 33 bytes. So it sees two requests in this stream, the first being what we have in green with that post request, and the body of this post request is shown in blue. It then thinks the second request in this stream starts in red there, and is a get request to the /doesn't-exist page. So it's going to cache the result of this request for the path /doesn't-exist. However, the backend server Abyss is going to read a mutated content length header, which says that the length of the request is 0 bytes, or length of the body is 0 bytes even. So it thinks that the second request in the stream starts in blue there, that request to /a.html with a header called something and a value it just doesn't really care about. And then again, it's a request as before to squid01.rslab. So just to show this in a diagram, we have Squid on the front end, reading the unmutated content length header and thinking the second request is to the /doesn't-exist path, and Abyss on the back end, reading our mutated content length header and thinking the second request is to /a.html. So Squid is going to cache the value of a.html under a different path. And this is a simple demo to show that cache poisoning exists. So how do we detect this black box? Well, we're working with detecting mutations here, and that's something we've already looked at. So we just need to modify our methodology slightly. So this might look fairly similar to before. We've got a post request, and the slightly strange thing about it is we have two content length headers, and one of them is mutated. Now we start off by setting the value of both of these to 0, and we get a 200 OK, and the response we expect for this post request. So we know that this is being passed as normal, and we haven't broken anything. Then we put an invalid value inside the content length header that isn't mutated. So this content length Z you see here. And unsurprisingly, we get an error. In this case, a 411 length required, as one of the servers in the chain has tried to look for the content length of this post request and not be able to find it due to our invalid value. So similarly, we try again with the mutated content length header. Now I'm showing this request with 0 bytes in both headers, again for comparison. But when we put an invalid value in our mutated content length header, we also get an error. However, it's a different error to what we saw last time. So we can infer that this error is being generated by a different server in the chain. So we now know that we have two servers, server A and server B. Server A is reading our unmutated content length header, and server B is reading our mutated content length header. We don't actually know at this point which is the front-end server and which is the back-end server. And this is very important to know this before we continue testing, so that we can continue testing safely and minimize the danger of affecting another user's request. So to find out which is the front-end server, we do something quite simple. We just send a post request with only one content length header, not mutated, and put an invalid value in it. We expect the front-end server to pass this request, as we expect any server to pass it, and we see a 411 length required, which we can assume is from the front-end server. Comparing to our testing earlier, this is the same as when we put this value in the unmutated header before. So we can assume that when we send two headers, it's the front-end server, in this case Squid, which is reading the unmutated content length header, and therefore the back-end server, Abyss, reading the mutated one. So we've got quite a good chance of request smuggling here, as we can send two content length headers and specify different content lengths in them, and the two servers that we're looking at will think the request has a different length body to each other. However, this doesn't guarantee request smuggling, and that's quite important to highlight. You actually need to continue testing. It's quite common in this sort of scenario for the backend server to actually be looking at both content length headers and continuing as normal if they have the same value, but as soon as you put a different value in those headers, it will complain and throw an error at you. So you can generate a timeout in a similar way to James Kettle's research by essentially starving the back end of content, and full details of that will be in the white paper, as well as some exploitation scripts. But the general advice from here is that you need to confirm beyond this, and often you have to actually just try exploit the system, which obviously you have to be quite careful about. So we've looked at some header smuggling, and the question is, how do we defend against this? Well, part of the defense I recommend is to use the tooling I'm going to be releasing as part of this research and scan any systems you're concerned about. Another piece of defense I consider key is on front-end servers, don't forward malformed or suspicious headers. So Cloudflare don't forward headers with a space in, for example, and that saves them from being used in the example earlier with API Gateway and the cache poisoning. And this is also the approach that AWS are taking to resolve this issue within API Gateway. They're writing a lot of tests to test the services within API Gateway to make sure they don't forward these malformed headers. There's also this concept that you should be quite liberal about parsing protocols such as HTTP. However, if it's for a backend server and you're expecting the request to be filtered or normalized by a front-end server, this doesn't necessarily apply, as you won't be seeing requests from all sorts of different implementations of HTTP. You should only be seeing requests from one implementation. So you can be a lot more strict, and that can help defend against these vulnerabilities. Now, in terms of future research, I think there are plenty more applications to be found. I'd recommend that you just go and scan as many systems as you can with my modified turbo intruder, find interesting behavior that you probably can't predict right now, and go play with it and see if you can exploit something. We've of course also seen a lot of HTTP2 request smuggling research this year, focused on HTTP2 to HTTP1 downgrades, and this has also led to lots of new ways to sneak headers through to the back end, with a focus on the transfer encoding header in general. So these techniques I haven't looked at as part of my research, but that could definitely provide some interesting results if you go and look at those. I've also made some assumptions in my research which are probably worth addressing. I've assumed that front and back end servers will give different errors to each other. I've also assumed that all headers are passed the same. So if you find one mutation that works with a content length header, we're assuming it works with every other header, which may not be true, although it generally seems to be. And I've also assumed that all servers pass the content length header in GET requests, which is mostly true, but there are definitely some servers I've seen which don't do this. So those will be missed by the methodology of this research. Now, there are some references here which I'd encourage you to go check out. These have really been informative in this research. There's also some other resources, which again, you can find in the slides. And if you found this talk interesting, I think you should probably have a look at these as you'll enjoy them as well. And thank you for coming. So links to our blogs there. I'd like to say a massive thank you to the AWS security team who've been really helpful and really good to work with throughout this research. And also we're hiring, so you have a bit of experience, come and talk to us. And are there any questions?